This work provides an architecture which uses a learning algorithm that incorporates single-depth images and tactile information to create rich and accurate 3D models. We use a three-step process. First, we create an initial object hypothesis using a depth-only CNN. Second, we collect tactile information to update the initial object hypothesis. Finally, we pass the combined depth and tactile information into a Visual-Tactile Fusion CNN to produce our final object hypothesis. Shown is a shoe on a table. We capture a 2.5D point cloud of the shoe from a single point of view. We voxelize the point cloud, shown here, of the object of interest and pass it through a depth-only CNN. The depth-only CNN fills the occluded regions of the object, as shown by the updated mesh, producing an approximated object geometry. Our CUDA-optimized smoothing algorithm integrates the CNN output with the original partial view to create a smooth, completed mesh. The completion is useful for planning manipulation tasks, such as grasping. Seen here, this system was able to successfully grasp an object using the depth-only completion. If more information about the object geometry is required, an exploratory step is performed where the end effector approaches the object to collect tactile information. The object shown has its handle occluded from the camera sensor. The tactile information concerning the handle is captured from a guarded move to the object. Here, we visualize the combined tactile and depth point clouds. The depth point cloud is shown in pink. The tactile point cloud, shown in white, was originally occluded to the camera sensor. This information gives the Visual-Tactile Fusion CNN more information about the object, enabling a more robust approximation of the object's geometry compared to a depth-only completion. Now, looking to the model of our Visual-Tactile Fusion architecture, we voxelize and combine the depth and tactile point clouds, and pass them through the Visual-Tactile CNN to produce an updated understanding of the object geometry. This Visual-Tactile CNN was trained on synthetic depth and tactile information. Our results show that the depth and tactile mesh captures the pitcher's handle, which was unobserved and missing from the depth-only completion. In summary, we created a platform that reasons about occluded object geometry in relation to an observed partial view of a target object and gathered tactile information. This system is fast because of offline training, uses multimodal sensory information, and requires no additional pose detection or localization.